Finally. Okay, thank you for your patience and thank you for being here. For me, it's a pleasure to present Sergi Plana. I met him almost 3 years ago in a workshop in Barcelona, and I was impressed by the things he's currently doing. He's unique, so he's the only guy who do electron crystallography here in Spain. And well, he did a PhD between Germany and Spain, and where he developed a new and super practical method for collecting diffraction patterns. And this new method ended up winning him several awards, including a Harold Rose Prize and a best thesis here in Spain and in Germany. After that, he worked in industry with nanomegas, okay, helping pharmaceutical companies like Novartis tackle complex crystallographic challenges, and even push to new territory with liquid phase electron crystallography. Currently, he's a senior researcher in Universitat Rovira Virgili in Tarragona, running a transmission electron microscope laboratory, and he's also teaching at the University of Barcelona. And well, I hope you enjoyed his presentation as much as I did 3 years ago. Now there are even more things, and he will talk about more things than he did 3 years ago. And with that, I'm done, and the stage is yours.
Well, first of all, thank you, Jaume, for this kind introduction. So I'm very happy to be here in this institute to just talk about one of my passions, which is basically electron diffraction. So what you can do with electron diffraction in order to characterize your materials at the nanoscale. So what I'm going to do today is basically that. So how we acquire this kind of data and which characterization we can obtain from this kind of data. Hopefully this works. Oh, okay. There we go. Right. So this presentation is divided in these 3 different blocks. So first of all, I will explain basically what we understand as electron crystallography, where we acquire electron diffraction data, or how it's beneficial in comparison to other emission sources. Then I will go deep into the details of the 3D electron diffraction technique. This would be equivalent to monocrystal, single crystal X-ray diffraction, but instead of looking at microcrystals, we look onto nanocrystals. And then we will change the technique, and we will go for this STEM, which is basically the mapping of an area of interest at the nanoscale, in which we acquire one diffraction pattern in each position. And by extracting information from this kind of data, we can really understand a bit more the physical properties of our systems. So let's start with electron crystallography. So where it is done? Basically, usually this is done in a TEM. So for the ones that they know that these are quite complex machines with respect to electron optics. In fact, this is one of the simpler ones nowadays, but still it's quite complex in a way. So basically what we do is we have our electron beam that goes through here. So here is the gun, it's going the electron down here. Here it's where we put our sample, and then this is transmitting, and here just down there, it's where the detectors are and where we acquire our diffraction patterns. So we are using electromagnetic lenses and coils in order to deviate the trajectories of electrons through the column, and it allows us to focus the diffraction patterns and the images in this kind of instruments. These are quite flexible machines because electrons can be accelerated between 30 kbs and 300 kbs. So this means that we have a span of wavelengths, electron wavelengths, that we can use in our diffraction applications. So as I said, the sample goes in this part here. So we have this kind of sample holders. And if you have a powder sample, the preparation is very easy. So we just take your powder, we have this kind of grids here, so we put the powder on top of this, and then we put it in the sample holder inside the TM, and you are ready to go, okay? So with these complex instruments, one logical question arises, and this is the question. So if there are dedicated and commercial solutions that only do 3D or for these STEM techniques, well, the establishment of the electron crystallography field has been along 100 years. So since the discovery of electrons, demonstration of electron diffraction, and the introduction of the 3D and for the STEM techniques. But it was not until the 2010s in which the development of new detectors that are more sensitive to electrons and also they are fast allowed the researchers to just collect data in a much more fast way, but also we could collect data from materials that were beam sensitive. And this is really important because for pharmaceuticals and organic crystals, this was a game changer. So nowadays, there are commercial solutions, but they are only focused on these specific techniques, while with the TEM, you can do much more other things. So for example, for a diffractometer that is only collecting 3D data, we have these two machines from two different companies, but also nowadays there is another dedicated microscope for 4D STEM applications from the Tescan company that it's based on this kind of analysis. So, which are the benefits of electrons and why we are interested in using them? Electrons interact strongly with matter. This is maybe intuitively a disadvantage, but it is an advantage because in principle we are more sensitive to detect light elements. Also, electrons can be focused at the angstrom scale. So we can have a very small beams in which we can illuminate nanocrystals, so we can go from microscale crystallography to nanoscale crystallography with electrons. And also another interesting thing is that the wavelength related to electrons is quite small, meaning that the Ewald sphere is very huge. So in this respect, then every diffraction pattern contains a lot of reflections, and if these crystals are aligned on a zone axis, we will get a lot of information from the zero-order Laue zone directly away. While if we tilt a bit, of course, we will have more Laue zones, orders of Laue zones in the pattern. But also, this is very interesting for the STEM, because with this kind of patterns, then we can understand an area of the crystallographic configuration of an area on systems that contain different phases. So we will see some examples of this as well. One of the things that I wanted to mention, and I said at the beginning, is that electrons interact strongly with matter. How much? If we look to the cross sections, we can see that for electrons, which are positioned here, are around 5 or 6 orders of magnitude higher than neutrons and X-rays. So it is a proof that electrons really interact much harder with matter. However, this also comes with a hint or advantage, which is that the probability of an elastic scattering with a crystal is higher for electrons than X-rays, meaning that, for example, if we send the same amount of particles to our crystals, X-rays will deposit more energy to the material than compared to electrons. Therefore, with this ideal comparable experiment, we will damage more our material with X-rays than electrons. Obviously, this is a bit counterintuitive, and also when you go to a TEM, the brightness, the flux of the electrons of the electron beam is quite high. Therefore, you always will have much more electrons going to your crystal. So, but to give you a picture, this is what you could obtain in a more theoretical comparison. Okay, how do we interpret the intensities that we have in our reflections? You could use the kinematical diffraction, so every electron or particle interact one time with your crystal. So we would have this typical formula in which intensity is proportional to the square of the structure factor for a given reflection. However, once again, multiple scattering events. So you could not consider the kinematical diffraction theory as a correct way to interpret the intensities that we have in the reflections. You could see this in an image. Yes, it's not forbidden to show images in a crystallographic talk. Yeah? So here we have a wedge sample of silicon. If it would be kinematical, there would not be fringes. But because of these multiple scattering events, we see fringes. So we can see directly that the complexity on how to interpret the intensities is a bit higher. Okay. So dynamical diffraction theory. This is what we do. So, or what we think that happens. So we have an incident electron wave that each beam can scatter more than one time through the crystals, and at the end of it, then we have our precious beams that we can collect the intensities out of it. And how you calculate these intensities, it's a bit more complex. I will not go into the details, so you have to use the Schrödinger equation. But mainly, you can have here a structure matrix that you can construct using the structure factors. And you have a scattering matrix here that it's pretty interesting. Why it's pretty interesting? Because the scattering matrix can be considered as an operator that is applied to the incident electron wave. So it's how the crystal will modify the electron wave that goes through the crystal, and this will provide you the diffracted electron waves. Also, the scattering matrix can be described as the exponential of the structure matrix. That's how you construct this. And then by taking the first column components, you can extract the intensities of the reflections based in this theory. There are programs that deal with this, and you can calculate the intensities in this way. But another fact of this is that, for example, if you take this exponential and you develop it as a series, a Taylor series, and you take only the first order, you recover the kinematical case. Well, if you extend it to further orders, then you start to see how the different beams, scattered beams, interact with each other. So you could consider 2, 3, 4, 5 scattering events happening in one single incident electron wave that is going through your crystal initially. Great. So with this, we're going to start with the precious 3D electron diffraction technique. What is it? How we collect data? This is very, very similar to what is single crystal electron diffraction doing. So we are just sending a beam to our crystal. We tilt our crystal, and in each tilt, we are acquiring a diffraction pattern out of this. So what we would see in a TEM is this image in which we have our crystal, and we want to put the beam into the crystal every time. And for every tilt, we collect a diffraction pattern. So this is how it would look like a raw 3D data from this kind of experiment. One of the barriers to overcome with this technique is the automation. If you do this with a TM that is not prepared for that, it may take 1 hour, 1 hour and a half. So automation is really key in order to get a more systematic and routine use of this technique in order to solve crystal structures. And this is one of the things that I've done in my PhD. So we developed an automated module that allowed to acquire this kind of data from 1 hour and a half to 10, 15 minutes. And well, if someone is interested, we have this as a digital micrograph plugin that is available in the GitHub repository, where we have as well other automation plugins that can be used for electron diffraction. Okay, so we have this raw 3D data here. What do we do with it? So we reconstruct the diffraction space. So we get this reconstruction here, in which we can see all the reflections and the distribution of intensity for each reflection. From this space, then we can index it. So we can obtain unit cells parameters that allow us to fit this lattice to all the reflections present in the data set, and also determine the Brebet lattice that is linked to these unit cell parameters. With this, we can then go to the determination of the space group. So this is typical as X-ray diffraction. So one has to go through different sections of the diffraction space. We can cut our diffraction volume to have these crystallographic sections, identify reflection conditions and extinctions. So here, for example, is a case of an orthorhombic structure. So we would go first for the 0 KL section. So what we can see here is that we have if I manage, so we have an extinction here, here, here. So here we have a condition, a reflection condition in that direction that needs to be K, even, so 2n in order to appear, while for the whole section, there is no extinction happening. For the H0L, we have once again here in this line an extinction similar to this one. But also here we see something interesting, which is that here we have weak reflections, right? So every two, we have strong, weak, strong, weak, strong, weak. And this is one of the consequences of dynamical scattering events, that some extinctions that should be there are not there when we acquire them. So this is important to take into account in order to identify the possible space group that this crystal may belong to. And finally, if we go to the last one, the HK0, here we can see that the reflections are appearing in a kind of yes, no situation in the whole plane. So we have an n-glide plane along the z-axis. And with these reflection conditions, one can go to the international tables of crystallography and identify the possible space groups that the crystal may be related to. Good. With this information, then we can go to any program that solves structures nowadays. So most of the programs nowadays include the electron scattering factors. You can obtain initial structure models ab initio by taking this information plus the composition of your material. Using different methods nowadays, there is also some artificial intelligence algorithms working to solve structures. And then you can perform kinematical refinement. Obviously, as I said before, the kinematical refinement is not, let's say, the most accurate way to describe the intensities of the reflections. So that's why there are some also other programs that allow you to make a dynamical refinement, so a structure refinement based on the dynamical theory of diffraction. And in this way, I encourage people to really go into this direction because the accuracy and the reliability of the crystal structures that you get is much better, makes much more sense. And this gives you, at the end, a better structure model of your materials. Okay, so you are happy with this. You go to the microscope, and then you get an ugly diffraction pattern like this one. And then you just want to don't work with electron diffraction anymore. So yeah, you have these situations in some cases in which we have a lot of different things produced by multiple scattering once again, but it's not included in the formalism that I have shown you. And this sometimes is painful to work with. So one way to get your data a bit more pseudokinematic is using a precessed electron beam. When we're using a precessed electron beam to collect a diffraction pattern, then we have this situation in which, for example, these Kikuchi lines are just smeared out, as very strong reflections that we see here. This is intensity redistributed to have a bit more intensity to other reflections that before were not seen. So this provides you a better way in order to analyze your diffraction data. So how do we do this in the TEM? So basically in the TEM, we just tilt the beam. So basically if this is the crystal, we tilt the beam and then we rotate it in this way. So making this precession movement. And then below the specimen, we sound counter-processing signals because if you tilt the beam, in the diffraction pattern, you will see a shift because the diffraction pattern is an angular space. So you need to recover that tilt to the same position in order to get as if it would not be precessed. Okay? So by doing that, then we can get these nice diffraction patterns that we see here. This is increasing the precession angle. So we can see how many more reflections are appearing. We have a more uniform distribution of intensities. And if we look into the geometric aspect, if you don't use precession, we have this, let's say, evil sphere, right? That when it intersects with the reflection, this is what we will see in our diffraction pattern. If we apply precession, we are effectively wobbling the evil sphere on the diffraction space. So we are integrating a volume in the diffraction space into our pattern. And for example, here we can see that by using precession, we are touching this reflection, while here we are not. And that's the reason why we see more and more reflections while we are increasing the precession angle on the acquisition. Great. So with this, 3D has been applied to any kind of material. Yes. So we have acquired, solved structures from inorganic compounds, organics, macromolecule structures, MOFs, SOFs, COFs, whatever framework you may think of. Also zeolites. And what I'm going to show you here is a couple of examples of my own explaining what the advantage can have in these different materials. So first we will go through small molecule crystals. In this case, it's about pigments and dyes. So we have this kind of molecules, all right? And what you do basically usually is going for a powder X-ray diffraction. And you get this kind of diffraction patterns. For the case of this orange pigment, we had even a high temperature phase. However, this was not possible to be used to solve the structure out of them. So it was very low symmetry. The crystals were nanocrystals, and the sample was also sensitive to irradiation. So what do we do? 3D, of course. So you acquire 3D data from this kind of crystals. We could retrieve ab initio the structure models of this. So this was a triclinic crystal system in P-1. So for example, for the pigment orange 34, here we could collect data at high temperature and low temperature. We could solve the structure in such a way that we could see that at low temperature we have this zigzag of the position of the molecules, while at high temperature the energy available could make the molecules to go flat, as we see in there. And for this perfect one, we were also able to solve the structure. So when I'm talking about ab initio, is saying that by introducing to the program the symmetry, the space group, the unit cell parameters, and the composition of the molecule that you know that is there, we could retrieve all the atoms that belong to that molecule. Okay, so what you are seeing here is the structure model that you can get exactly as if it's output by direct methods in SIR 2014. So that's why, for example, here we have a blue and black atom that should be all carbon, okay? Why I'm showing this as well is because we can use electron diffraction to detect experimentally the position of hydrogens. So in the case of the red one, we were able to detect one of the hydrogens available at the ethanol group. Obviously, you don't care to see the hydrogens of benzene rings because you know that they have to be there with a specific geometry, and that's not really interesting. But if you are able to see hydrogens that could explain, in this case, intermolecular interactions, then you have an experimental confirmation that that was happening. In the case of the orange pigment, we could as well say here or determine the tautomerism of these molecules. So in this case, this hydrogen could be positioned here or here attached to the oxygen, but with the 3DED, we were able to determine that in this case, the hydrogen was positioned into connected, let's say, to the nitrogen atom in both cases. Okay, we change a bit the topic and we go to cement. Cement is produced by mixing a clinker, which is the main constituent, plus several calcium sulfates. However, here what we have is usually if you go to powder X-ray diffraction, at least for only the clinker, you have a mixture of a lot of phases. So you had this nice powder X-ray diffraction, and the industry is using this in order to quantify the different ratio of the phases. This allows us to determine the different phases. This will result in different properties of the cement, so this is really important. However, if you want to make, if you really want to make single crystal analysis from this data, it's really difficult because you have a lot of reflection overlapping. So 3DED comes here to the rescue because you can really have a very small beam into you can have your phase mixtures, put it in a grid, and just analyze the crystals that you are interested in. So by doing this, we analyzed the commercial sample, and we saw that for a specific polymorph of the calcium silicate, we had some satellite reflections. So we could determine the average unit cell parameters that was fitting nicely to the literature. But if we would look closely, you could see that this was a main reflection, but there were some satellite reflections that were positioned at an incommensurate distance with respect to the main satellites. So with this, you could as well solve more incommensurate modulated structures. Okay, so in this case, we can perform in the same way that we have done so far. So we can reconstruct the diffraction space. We can, here in this case, we need 4 Miller indices considering a 1 modulation wave vector. So in this way, we can fit or index all the reflections present in this diffraction space. We can cut different sections, identify reflection conditions, obtain a super space group, and finally solve the structure. Okay, I will not go into much details. I don't want to bother you too much. So basically what you can do here is just see the distribution of possible position of the atoms along the wave vector. So basically, since the wave vector here is along the a-axis, what you have here is basically all the possible positions that the atoms can have in these configurations. So if you would look at in the real space. So with this, it's just an example on how you can also use 3D to go beyond the typical average structure determination that you may have with more typical samples. Okay, another cool thing that you can do with 3D is determination of chirality. Because of multiple scattering events, of course, the Friedel law is not fulfilled. So the intensity for a reflection of G, of a reciprocal vector, will not be the same as minus G. And this allows us, by using the dynamical refinement, to determine chirality. So here, this is a work that was done, or we are doing with a PhD student at Madrid, Jaime Jurado Sanchez. He is synthesizing chiral zeolites. And what we wanted to see if what they expected to be racemic, so 50-50 of both different structures, or if it's an anti-pure synthesis. So you could do 3D by acquiring a lot of data from different crystals, do this analysis, and understand if we have really a racemic or an anti-pure synthesis of this material. So by doing this, we just saw that when they expected a racemic synthesis because of chemical reactions and chemical tests that they did, we could really see that around 50-50 of the crystals are one or the other chiral space group, while for the anti-pure synthesis, we can really see that for one of the chiral space group, we always have lower figures of merit, and therefore we can determine with really a lot of reliability that we have an anti-pure synthesis. Obviously, the limiting point is how much crystals do you want to acquire here. This is an analysis of 11 and 12 crystals respectively, but this could be done in a much more automated way as well. Great, so now let's talk about natural minerals. Usually, minerals tend to be layered materials, okay? So we had this new mineral that was, well, all this characterization was done by Jordi Ibáñez, here present in the audience, in fact. So this is a new mineral that was obtained from the Republic of Congo, and now it's sent to be approved as a really new mineral. So they got this piece, and from this area, they could got from powder X-ray diffraction, well, scratching a bit out of it, but well, a bit, quite a lot. They were able to obtain a very nice structure from this material. So we have these structural layers here, and then we have these interlayer components that are, let's say, fixing the structure in this A direction. So Jordi went then to my colleagues in the Universitat of Barcelona to just collect some yields data out of it to determine the oxidation state of this material, and they got this stem Hadef image. Problem here, the powder X-ray diffraction structure was not fitting to here. So this structure was not corresponding to this image. It could not. Therefore, if you do 3D, then you can obtain the structure from this exact region. So we did that from these and other crystals from this ore, and we were able to see that in some cases, the unit cell parameter, the one that is perpendicular to the structural layers, is much smaller. Okay. Also, we could see from crystallographic sections of the diffraction space that the direction perpendicular to the structural layers contain diffuse scattering. Therefore, the position of the layers is not fully periodic, but it has some movement, some difference that makes the diffraction pattern not coherent in that direction, and that's why we'll start to see these diffuse streaks. However, we can manage to avoid that somehow, and we could obtain a structure model out of this that then finally we could explain this stem Hadef image quite nicely. And finally, for 3D, we can also use it to understand the epitaxial structure of heterostructures. So this is a system of silicon, quartz, and zinc oxide. So we can go to the TEM, we can get this image, we can collect 3D data from the 3 different components, we can reconstruct the diffraction space, found the unit cell parameters in reciprocal space, go to the real space. So at this point, we already know how each box fits into each other. And from there, then we can really determine the pitaxia of this heterostructure. So this is really very interesting because with the stem HDF images, you can see one, let's say 2 dimensions, but sometimes the devil is hidden in the third. So by doing that, you can really spot some difference that you may have and you may not expect by only just having an image out of this. Okay, up to now, we have described what is 3D and some examples. Therefore, what I have shown is that with 3D we can do cool stuff, right? So, for example, for organics, we could detect the hydrogen positions. For these heterostructures, we could determine the epitaxia. For chiral zeolites, we can determine the chirality of this in every crystal that we have in our sample. From cement, we can determine, or we can go beyond the typical structure solution or structure determination with incommensurate modulated structure. And with minerals, we can, or layered materials, we can understand a bit more what's happening between these layers that are weakly bonded. So now it's a different technique, and this is the one called for the stem. Typical stem relies on acquiring an intensity for each pixel. So when you go to the TEM, we have the beam, and you perform a stem. Okay, this beam would be a scanning, but in each case, we have some detector here that, depending on the angular position in which we detect the signal, then we can obtain different images. And for example, we can have this very nice image of Ipaco, it was, right, from Jaume, in which you can really see all the atoms. So he sees in real space, I see it in diffraction space. Then, now, for the stem, what do you do here? Basically, in every pixel that we have here, we acquire a diffraction pattern, right? So that's why it's called for the stem, because we have 2D scanning in real space and 2D of each diffraction pattern that we have. So 2 + 2 is 4. So that's why they call it in that case for the stem. And what you can do with this kind of diffraction data? First, we can obtain phase and orientation maps. For example, we have this reference stem HDF image here, and we just want to collect some for the stem data from this area. So we collect that. This is how it would look like as a bright field image. And in each pixel, as I said, we have these nice diffraction patterns. Since we are using a smaller beam, it has a bit more convergence. So that's why we see disks instead of spots. And this is a typical case for the stem. And then with these diffraction patterns, and knowing which phases do we have in our samples, we can calculate or simulate diffraction patterns based on the kinematical theory of diffraction, but this is more than enough, in order to fit which is the simulated diffraction pattern that fits best to the experimental ones. So this is what they are called template matching algorithms. So by libraries of simulated patterns, we can compare and find which is the one that fits best to these experimental diffraction patterns. And by doing that, then we can obtain the phase map. So we can determine where are, for example, in this case, hematite, quartz, mullite, and a spinel. And also we can get the orientation map. So we have a lot of colors here, but basically, if you focus, okay, this is red, it's not the best, but okay, let's focus in this one with this spinel here, these crystals here, which is just pink. So pink is related to the phase of a spinel. But if we look here, it's also pink, unfortunately. But the idea here is that this color represents a symmetrically independent reflection related to the Laue class of that structure. Okay, so these color maps that you have here represent the symmetrically independent directions that are related to the Laue class that belongs to that phase. And by doing that, we can have these nice colorful maps that maybe here is not interesting, but in other systems can be of relevance. What else we can do more? We can do strain maps. So in this case, we are checking how reflections are changing with respect to a reference. So for example, we have here this position of the reflections, and we can see that when it crosses the interface, they shrink a bit, okay? So when we know how the scan reference system belongs to the diffraction pattern, we can then calculate the different strain components. So in X, in Y, let's say, shear strain, and then the rotation, okay? So by doing this, then we can, for example, in this case, which it's not really interesting, but the idea is that we can see how the shrinking is happening in this direction. That's why we have this high contrast or gradient here. While for the other direction, in this direction, or in this direction, or in this rotation, we just have noise, okay? But in this way, we can calculate strain maps out of these kind of materials. Also, you can map electric and magnetic fields. So if you shoot a particle charge across an electric or magnetic field, these fields will deviate their trajectories. So in this case, what we would do is just monitor how the whole diffraction pattern is shifting. And by doing that, we can extract electric and magnetic field properties out of our materials. So for example, we could just obtain values of the electric field from quantum wells, or if you have a magnetic material, we could determine the magnetic domains that are present and how the magnetic field is in that kind of particle. Once again, what's the benefits of precession here? Well, we have seen that in some cases, the diffraction patterns are not so nice. So therefore, the template matching algorithm may not work if you have a lot of Kikuchi lines, for example. So we can see here that by using precession, the uniformity of what you expect that it should be, it's much better. But also for strain maps, since we have these disks, the intensity inside the disk tend to be not uniform because we have multiple scattering events that make this kind of lines. But by using precession, we can have a more uniform intensity inside the disks. And this is key in order to identify these different relative positions of the reflections that allow to calculate these strain maps. With this, I will go through some examples. Hopefully, I'm on time. So this first one is about ancient ceramics, which we are basically mapping the different phases in order to understand the manufacturing process of this. So we acquire a stem Hadoop image, for example, from this area. We can collect elemental maps from this area to understand the different elements that we have, and we can obtain a phase map out of this. Once again, we need to know beforehand which phases do we have. However, there is an outlier here, which is this one up to the top. So there, we can see that the program has identified these three different materials in this area. We don't have iron here. Apparently, if we look to the other EDS maps, we could see that there is titanium there, but we didn't know which one. So what do we do here? We do 3DD. So we will know for sure which crystal structure would belong to this particular crystal. So we did that, and we saw that from the analysis of the Brebet lattice, as well as the different sections and the symmetries, we could intuitively say that maybe it's anisovite. It's a titanium oxide that is produced at very high temperatures. We could confirm the structure by solving it and refine it dynamically. And then we use this structure as it is now to simulate this template of simulated patterns. And then finally, we could see that the program then very nicely identifies these three different crystals that before were not so clear that they are really this phase. So you could combine the techniques in order to get a better picture of your materials. Another field in which it can be beneficial, the 4D STEM can be beneficial, is to visualize crystalline domains in thin films. Usually, if you go to a TM, a high-resolution STEM microscope, you would get something like this. And then you ask yourself, okay, do we have more than one crystalline domain in this image? If you look carefully, you may be able to see it, but it's really difficult sometimes. But with diffraction, if the patterns are quite different, then you can differentiate them. So if we do that, we just discretize the position of the beam in this image, for example, and you acquire diffraction pattern in each position of this, we can start just here and we have this nice pattern. So if we continue scanning, there is this other pattern here in which is a bit different. It contains the same, some of the reflections are positioned in the same position, but others appear that are not in the other. And you can use that in order to identify the different domains. So if we continue in this, then one can really identify where is the grain boundary in this case of these different domains and understand a bit better these kind of systems. So in this respect, we did some work in thin films. This is an example of a 100 nanometer thin film. That was a collaboration from here for ICMAB, in which, in this case, they only had 3 different domains. We could really see that the diffraction patterns are a bit different for the 3 of them. Okay, unfortunately, blue is a bit blurred. But the idea is that you can use that in order to see if, for example, we have a more presence of one of the domains or the other. So we could see here that for a specific orientation of the substrate, we have a predominance of a given domain, while for another orientation of the substrate, we have more mixing of these different domains. And this could explain some optical properties that this material had. Also, we can go smaller in size, higher in resolution, let's say, which means that, for example, in this system in which we have 10 nanometer lanthanum iron oxide, we could see that by using different substrates in which the characteristic lattice parameter differs a lot or not that much according to our system under study, we could see that by using subsets that are approaching the characteristic lattice parameter LFO, we could see how we have domains that increase in size. So we can see directly or understand directly how these films are grown on top of each other, understand the granularity, if you may, of these thin films. Also, once again, here we had 3 different configurations possible, and that's why we could do this more 3 color maps out of it. Another point is that we could get strain maps out of this area. So we could have a statistical analysis of very large areas of our materials, our thin films. This is the case of the LFO on the Lao substrate. So we have this pretty large area of around 650 nanometers. And in each case here, we have the components, the strain components. And since the mismatch of the characteristic lattice parameter was that high, we had a lot of dislocations. So one can see here very nicely the position of the dislocations, have some statistics out of this, and get some intensity of how disordered this material is. Okay, finally, hopefully Jaume will not kill me, is about the mapping of electric fields. Okay, so I will show you a quick example on the system of the interface between Lao STO. In this case, it was published already that there was some accumulation or distribution of charge at the interface. So we could see that here, for example, in the Lao STO interface, we have an accumulation of charge along the STO area. This is because you have 2 different materials that have a different work function. So the energy bands need to be adapted. So there is this electrostatic mismatch that creates the possibility to have this charge distribution at the interface. This was done with electronography, a very specific technique that is done in a TEM, but you can use as well for this STEM in order to map these things. So we did that in a similar system, let's say. So we have here for the STEM data, once again, each pixel belongs to a diffraction pattern. We could see as well here how the use of precession really helped. We had these lines here appearing that are really distracting a bit to what we want to see. But with precession, we have these very nice uniform intensities. And what we are visualizing in this image is just the transmitted beam to see how it's moving, the transmitted beam, when we go through the interface. So now we have the pattern, the transmitted beam here, we are going through down, and you can see at some point how we have this shift. So we can monitor that shift and obtain the electric field related to that movement. So we could really see that at the STO region, we had this high electric field. And by calculating the charge density, which is just the divergence of the electric field, we could really determine experimentally the visualization of this charge at the interface. Okay. Great. So we arrive to the conclusions. Hopefully you get a sense of what electron crystallography can do. And I wanted to just send some take-home messages from this. So first of all, TEMs are flexible electron-optic machines that allows you to carry out a lot of electron crystallography characterization. The main problem is the automation. These techniques, nowadays there are commercial solutions, modules that you can buy in your standard TEM, but the automation is key in order to have more systematic and reliable results out of this. In that respect, I have some scripts done and some plugins available in my GitHub repository. But what I want to send the message is that all TMs can do electron diffraction. So think about that in order to make some electron crystallography out of your materials. Then 3DD is a technique, I think, to go for the characterization of nanocrystals. If you have a big piece of crystal or not that big, for sure go for X-ray diffraction. Doesn't need to go everything to electron diffraction. Even if they are very big, you will have to to just crush it. So don't do it, right? So you just go to X-ray diffraction and you do it. But when you have very small things, nanocrystals, for sure electron diffraction can really help you in order to determine the structures for these materials. Then for the stem or the variant with precession allows you to characterize or obtain information in an area. So you have crystallographic information from an area that can help you to elucidate let's say the relation between the crystallographic structure and the properties that the material can have. And finally, the combination of these two techniques is the ideal platform to characterize any materials that are, let's say, structured at the nanometer scale, and this allows best, let's say, crystallographic characterization of this kind of systems and materials. With this, I thank you all for your attention. Hopefully you are not really bored, so I'm happy to answer any questions that you may have.
Okay. So now it's time for questions in the audience. There's anybody have the question? No?
Thank you very much, Sergi. It was wonderful to see all these possibilities of these techniques. I have a very simple question. You mentioned that the possibility of mapping electric and magnetic fields, right? So which is if you want to do this kind of mappings, and you know we are interested in electric fields, which is the energy of the electrons that are probing the material? It's in the range of...
Well, you can... The energy of the electrons that go through the sample, you mean? Yes. Well, this is depends
on the voltage. I mean, you apply.
So you can apply. For example, with our microscope interrogona, you can apply from 80 kVs to 200 kVs. Energy in joules, I'm not so sure, but
so kilo
electron volts, yes.
No, because I was wondering if your objective is to distinguish between electric and magnetic fields. You can have relativistic effects or not, because a few kilo electron volts, yeah, you have the electric field, but in the rest frame of the electron, you have a magnetic field, effective magnetic field. I don't know if it is necessary or not. Well.
So first to disentangle. So for example, if you have a magnetic material also that you can bias it, for example, it has electric and magnetic field, there are ways to differentiate the electric and magnetic field for the sample, but then the microscope has to go into a different state. With respect to to if the electric or magnetic field of the electron can affect this measurement per se. I'm not sure. So only taking into account the classical approach of the Lorentz by seeing how it just moves the transmitted beam, this is okay. There is a quantum mechanic approach in which you can see that there is a momentum transfer inside the intensity of the beam. I don't know if in that case considers the relativistic effects of electrons, but you can see as well that even if the transmitted beam, the disk itself is not moving, the distribution of intensity inside the disk is moving, and this can be simulated, and you can see that this is moving. So I'm not so sure if that framework considers.
I was making some mental, very simple calculations, very simple. Maybe we can discuss later, but for a few kiloelectron volts the correction should be really small. But at some point, maybe we can discuss later. But thank you.
I remember that in 2013, when I tried to process data of organic compounds with 3D electron diffraction, there were problems with some organic compounds. I think that I know that later one way to reduce this problem was to do a sequential scan to reduce the time, the scanning time, and but I don't know if how now the situation is with organic compounds. Because this is an important issue in the case of the pharma industry. No?
Yes, so things have developed a lot in the sense that the sensitive detectors are more available, so you can really set your electron beam to have a very low electron flux, so you can have the minimum interaction with your crystal in order to get significant electron diffraction data out of this. BEM sensitivity is really a problem. So for organics, also for MOFs and other more fragile material, definitely. But if you have a system in which you are illuminating your sample only when you need it, and then you have a sensitive detector with this, coupled with a very low electron beam, low bright, well, not that bright electron beam, then you can obtain diffraction data. In the worst case scenarios, now you can also get data from several crystals, and you can merge all of this electron diffraction data together in order to increase the completeness. And this helps in order to solve the structures. But the key point is the introduction of direct detectors that allows you to work at very, very low electron doses with significant data out of it.
At that time, one possibility was to look for fissure zones that were not damaged. No?
It's true that, so one thing that you could do if you see that it's a big crystal that you can just scan the beam into different areas of your crystal, you could do that. So there are different types of possibilities in order to solve this kind of material.
But now the preference is to look for different small crystals, yes, instead of looking a big one, different zones.
Yes, no? Yes, I would say so.
Thank you. The resolution of the data reach normally atomic resolution, or is below atomic resolution?
Depends on the crystal structure. So for inorganic materials that are quiet beam stable, you can reach 0.5 angstroms, so 2 reciprocal Armstrong resolution. So, but it depends on the structure.
But you have the same problem then with X-rays.
Yes.
This is a general problem, yes, of the crystal.
Correct.
Okay, thank you.
Regarding the dose, and possible damage. There's also these new electrostatic blankers that allows you to control the dose, okay, on your sample. These are quite neat. They are not in every microscope, but in a few years there will be. Yeah.
Thank you for the talk. Regarding the imaging of domains,
okay.
You need a Lorentz lens. I mean,
magnetic domains.
Magnetic domains. Yes.
So you need. So obviously, when the position where you put the sample in the objective lens has usually a magnetic field of 2 Teslas. It's huge. So this will preclude you for any magnetic measurement. So you need to work in a state of the microscope in which this is switched off. So this is a Lorentz setup.
And is there any microscope around that can do this? From the many new microscopes that
what is around?
I mean, well, in Spain.
I'm not sure.
Yeah. Okay.
Lorentz microscopy?
Yeah, in Zaragoza.
Zaragoza. Okay. And it's possible to do for this stem?
I don't know.
Because
to do Lorentz microscopy with a stem.
For this stem.
For this stem.
For this stem and Lorentz microscopy.
Well, I understand that to image magnetic domains doing for this stem, you need a Lorentz. Otherwise, you are not seeing the.
So you could.
The state that is, let's say, without saturation.
Yeah. You could. The problem is that usually magnetic domains are visualized through DPC. So DPC and for the stem are different in the sense that DPC use segmented detectors, not pixelated detectors, let's say.
So you see the helicity? No, what is the DPC?
DPC is just taking the differential phase contrast. So earlier works were done like this. If you do for the stem with the objective lens off, you could do that. But the resolution that you may have may not be that huge. That's the problem. Okay. Nevertheless, nowadays there are exotic things. So there are magnetic lenses that do not have a magnetic field in the sample, and you can go to atomic resolution in STEM. Yeah, there is only one maybe in the world, but it's coming.
Okay, thank you.
It's not going to be. So the first one and unique so far is the one in Japan, but I think in US there are two centers that both won. So far there's only one available and up and running. But you can cancel out the magnetic field of the objective lens and perform this kind of experiments.
At atomic resolution.
At atomic resolution, yeah. Any other questions?
It's only for the 3D electron diffraction, how many images do you need to acquire approximately for determine the space group? And
depends on the symmetry of the crystal. So if you have a cubic material, maybe you can acquire a diffraction data between -30 and +30 degrees. So this would mean 61 patterns if you use a tilted step of 1 degree, and this may be just enough. But if your symmetry is decreasing, then you need much more. So usually what I tend to do is to acquire the most data possible in everything that we measure so that we are not constrained by that fact. And even if, for example, it's a monoclinic or triclinic structure, which requires a lot of volume in the diffraction space to be sampled, then you can do this thing of merging different crystals, the data from different crystals, and this allows you to increase the completeness, and you may have more chance to solve the structure.
Yes. Thanks for the talk. Very, very nice. I haven't understood one of the examples. Well, you have shown the distribution of orientations, but I didn't understand very well. This is done. This is automatized. This is all. You mentioned that you need to connect to a database, or not. Can you explain a little bit more how can you generate the maps of the distribution of the orientations?
What is this? Hello. Okay. So yes. So basically, this works still. Or? Okay. Yeah. So here we have the 40 stem data. Every pixel, one diffraction pattern. So what you do is generate a library of simulated electron diffraction patterns. So you have some programs in which you can input the CIF file, and then automatically it generates a set of patterns in the different directions corresponding to the lower class of that material. And then the program, the algorithm called template matching, there are others, but just for brevity here, I'm just showing this one. Then the algorithm just look for the simulated pattern that fits best to the experimental one. And the one that fits best is the one that the program will give you as the orientation and phase of that pattern. And by doing that for each pixel, then you can recover the phase maps and the orientation maps.
It's a program of a database. This is a program.
This is a program. It's a program. It's a program. No, it's not. Yes. Yes.
It's not in X-ray. The spots are not don't belong to a zone. No?
Yeah.
And then it's done automatically and safer.
Yes. Yeah. Another thing is that if anyone is knows EBSD from NSEM, it's the same thing, but at the nanoscale.
Okay, thanks. Those online, let's give them a chance. There's anybody that has a question, please write it down in the chat. I saw Pep raise the hand. I don't know if he's... Oh, rara.
Pep Foncuberta.
Yes. Permitir hablar, ¿ya? Pep? No? Okay. Okay, if there's no more questions. Before Sergi again, I would like to remind you that next July, the 10th and 11th of July, it's a Thursday and Friday, there's going to be a STEM ILS school, okay? We invited really good speakers, okay, from above, and well, they will talk about this spectroscopy, electron energy loss spectroscopy. So it's going to be in June, the 10th and the 11th. And I think it's going to be July, sorry. So, yeah. Not June, July, yeah? 10th, 11th. Okay, and with that, thanks. I would like to thank again Sergi, the speaker.
Thank you.